Okay, I'm going to repeat the start of question 46 because I realized I didn't finish it in the last video. The negative angle identities, remember what they refer to. If we have a positive angle x that rotates into quadrant 1, then the opposite of x would be the same size triangle in quadrant 4 right below it, or likewise they would be in quadrants 2 and 3. But directly above each other. So the negative angle identities are really very simple. If you think about the sign of this negative angle, isn't this y coordinate in quadrant 4 the opposite of the y coordinate in quadrant 1? So the opposite sign comes out in front. How about their cosines? The cosine of this negative angle is exactly the same as the cosine of the positive angle. So the negative sign simply drops out. How would tangent work? These two angles in quadrant 1 and quadrant 4 would have opposite tangents. So tangent works like sine, where the opposite sign would come out in front. And then for their reciprocals, their reciprocal matches up with the ratio itself, so doing a reciprocal doesn't change the positive negative value. So the only ones where the negative sign drops out would be cosine and secant. But for all of the others, the trig ratio of a negative angle is the opposite of the ratio of that positive angle. So in letter G, what can we conclude? If we know the sine of 17 degrees, then we know that the sine of negative 17 is the opposite of A. What do we know about the cosine of 147 degrees? That's interesting that that angle is in quadrant 3, 147, so the opposite would be this direction. And again, do you see that their cosines are directly, the angles are directly above and below each other, so their cosines are the same. So the cosine of negative 147, let me write that again, would be the same as B. We don't have to do any sign change. Okay, let's verify some trig identities. Remember, the idea of verifying an identity was that we didn't want to cross over the equal sign. We want to convert, using our trig identities, we want to convert values on one side to the other until the two sides match without ever crossing over. So we could replace, for example, 1 plus cotangent squared. Do you recognize that as a Pythagorean identity? I hope you recognize that, and it might take a little bit of work, but do you eventually change that to cosecant squared? And now if you look at these two values, tangent times cosecant, are you suspicious that maybe something would cancel? So converting to sines and cosines was another one of our common methods here. So let's rewrite tangent squared by its definition, sine squared over cosine squared. And let's rewrite cosecant as the reciprocal of sine squared. And you can see what I mean about something canceling. So now we have 1 over cosine squared x, and we would probably rewrite that as secant x, secant squared of x. So let's see on the other side if we can turn this into secant squared of x. Well, again, look at the denominator. Doesn't it look like a Pythagorean identity? If sine squared plus cosine squared is equal to 1, isn't 1 minus sine squared equal to cosine squared? So you might have to write out a Pythagorean identity, but you should know these pretty well. And now we recognize this, of course, as secant squared x. So not too difficult. All right, for letter B, same idea. How can we verify that these two expressions are equal? Well, clearly the right-hand side is already simplified, so I think our goal here would be to work on the left-hand side. So how could we rewrite this? And you don't have to show every one of these steps, but I'm going to split this up here so everyone recognizes what I'm going to do here. Do you see that I just took the denominator out, factored it out of the numerator? Because what is 1 over cosecant squared? That would be, if we flip cosecant squared, it would, or not squared, just cosecant. If we put it back to its reciprocal, this would be sine of theta. And what is cotangent? Cotangent is cosine over sine. And again, we verified that cosine theta on the left side is indeed equal to cosine theta on the right side. So that's the idea of verifying identities. All right, one of your favorite problems was using sum and difference identities. These formulas you do not have to have memorized. If it shows up on the final exam, the formulas would be given. So we might get a question like number 48, which doesn't require too much time here. Just look at what we've got. We've got sine of one angle, let's call that A, times cosine of another, you could think of that as B, minus cosine of angle B times the sine of angle A. Oh, I think we've got that maybe written. Notice I didn't change these. I think this is another typo I've got to change on our review sheet. We've got cosine of 12 twice, and I think it should be the other way around. So I think I have to fix these. I turned both of them around, and this should still say 50, and this should still say 12. So this would be A and B. So in any case, can we match it up to a formula? Do you see here that we now have sine of one angle times cosine of the other minus cosine of the first angle, sine of the second. So I think it matches with this formula. So I think this matches with the sine of 50 minus 12, and of course that would be the sine of 38 degrees. So sorry about the typing error there in number 48. All right, use a sum identity to find the cosine of 75. We don't know the cosine of 75, but we do know that it's made up of two of our special angles that we do know. We do know the unit circle for 45 45s and 30 60 90s. So let's set up the cosine of a sum. So let's go up here and let's use this formula, cosine of a sum, and let's let A be 45 and B be 30. So this will be cosine of 45 degrees, cosine of 30 degrees, minus sine of 45 degrees, sine of 30 degrees. And then let's fill in the values that we know. We know that this is 1 over square root of 2, or in rationalized form, square root of 2 over 2. Cosine of 30 is 1/2. Sine of 45 is also square root of 2 over 2. Sine of 30 is square root of 3. Oops, try that again. Sine of 30 is 1/2. And sorry, I just lost a 2 there. All right, so if we multiply, we get, for this first term, square root of 2 over 4. And for the second term, we get square root of 2 over 4. And I clearly know 0 is not the answer. So I have to find my mistake here. And I think I see it right here with cosine of 30 degrees. Let's think about cosine of 30 degrees. Shouldn't that have been square root of 3 over 2? So there, we caught my mistake. So this numerator in the first part, square root of 2 times square root of 3. Let me fix my mistake here. So I think we would come up with square root of 6 minus square root of 2 over 4, if I've fixed my arithmetic mistakes. If I'm not thinking here while I'm talking, you guys can adjust my arithmetic, but I think that fixes the mistake. All right, now we've got some Pythagorean triples here. I see that the cosine of some angle is 4 over 5. And we are told that angles S and T are in quadrant 4. So if I want an angle that has a cosine of 4 over 5, remember cosine would be adjacent leg over hypotenuse. So I would be thinking of a triangle, a 3, 4, 5 triangle in quadrant 4. So this would be my angle S. And we know that the sine of angle T is negative 12 over 13. And it says that is also in quadrant 4. So sine is opposite leg. That would be the vertical leg over the hypotenuse. So let's see if I drew a 5, 12, 13 triangle here. The 12 would be negative. Up here, by the way, this 3 would be negative. So this would be our angle T. Now you don't have to draw a diagram as long as you're thinking of these Pythagorean triples. But do you see how easy it is for us to fill in these missing angles? If this is angle S and we knew that its cosine was 4/5, look at its sine is opposite leg over hypotenuse. So you might have recognized that without having to draw the triangle. The cosine of the other angle, the cosine of angle T, would be the adjacent leg 5 over the hypotenuse 13. And now we're asked to use our sign of a difference formula. So you're going to go to your research page, or you can scroll back in the, you got this printed on your handout. So the sign of the difference is the sine of the first angle times the cosine of the second angle minus the cosine of the first angle, sine of the second angle. And now we can fill these in because we've done all the work. The sine of angle S we just decided was negative 3/5. The cosine of angle T, 5/13. The cosine of S was given, 4/5. And the sine of T was given, negative 12/13. And notice you're always going to have a common denominator when you do these. Our denominators match up in reverse order. Here we have a negative times a negative, so I'm going to make this a positive, 48 over 65. And a negative and a positive, so let's do the difference here. Looks like we'll have 33 over 65. And if there's a common factor, you can reduce that. But there is our answer. All right, question 51. Use your trig identity handout or page 834 of your textbook to name the type of identity used below. Okay, and this one I just wanted you to be familiar with. Again, I wouldn't put this on the semester exam without you having the resource page handy. But this is a formula that you'll use often in higher level mathematics. So I wanted you to recognize the double angle formula. So 38 is twice 19 degrees. So we've got a formula then that says if we can cut that angle in half, that it is 2 times the sine times the cosine. So it's a nice identity that's used in calculus to simplify, but not too big a deal here on your final exam because you are not expected to have memorized that identity. All right, I think we're going to pause here and then pick up in the next video with question 52.